Good morning, dear students. I'm Dr. Hemalta KS, Assistant Professor, Department of Physics, Mahani Science College for Women, Bengaluru. Having learned various concepts of nuclear reactions in the previous sessions, today I'm going to explain the concepts of nuclear reaction cross section and a problem related to it in this particular session. A measure of the likelihood of particular interaction. This statement has inner meaning of nuclear reaction cross section, what exactly it is. You will understand this as we move on further in detail. In nuclear physics, the most effective way to understand the nucleus is by studying the nuclear reactions by bombarding the particles to collide with a stationary target nuclei. Nucleus is a very tiny object with the vast majority of the space inside it is an empty space, as you know. In that case, when the incident particles are bombarded to pass through the target nucleus, vast majority of the incident particles usually penetrate through the empty space of the nucleus. Only small amount of incident particles actually interacts with the target nucleus and leads to some kind of nuclear reactions. The probability that a bombarding particle will interact in a certain way with a target nucleus to give rise to some sort of nuclear reactions need to be understood on the idea of cross section called nuclear cross section denoted by sigma. Idea of this cross section also facilitates to calculate how many incident particles can penetrate through the material. This leads to simple definition of nuclear cross section. A nuclear cross section is simply defined as an area around the nucleus on which if an incident particle is incident definitely moves into it and leads to an interaction with the target particle or nucleus. All the other incident particles outside this area will penetrate through without interacting with it. So, with this definition, let us consider some important factors which are going to influence the nuclear cross section. It depends upon the kind or nature of the incident particles. The incident particles could be electrons, protons, neutrons, or deuterons, and so on. Firstly, when the incident particles containing protons, which are being positively charged, is incident on a target nucleus, it is repelled by the nucleus away from it. So here, the nucleus which is being associated with the positive charge, as the protons move towards it, repels it away from it. So it is very difficult to induce a nuclear reaction between protons and some sort of a nucleus. Therefore, this area of cross section corresponding to protons will be less. But when you consider the case of neutrons, being a neutral particles are not repelled by the nucleus. Vast majority of the neutrons which comes near the nucleus will interact with the nucleus. Therefore, area of cross section corresponding to neutrons will be higher. So let us move to the second factor. It depends on the energy of the incident particles. Fast moving neutrons and slow moving neutrons, also called thermal neutrons, will have a great influence on the area of cross section or nuclear cross section. So if the velocity associated with the neutrons are very high, they are moving likely to penetrate through the nucleus without interacting with it. But if you consider slow neutrons or thermal neutrons with lower velocity, when they are incident on the target material, thermal neutrons being associated with higher de Broglie wavelength more likely interacts with the nucleus. So here you can consider the de Broglie wave equation or wavelength expression lambda is equal to h by mv, and v is smaller in case of thermal neutrons or slow neutrons. That indicates the wavelength associated with it will be larger. So the de Broglie wavelength associated with the thermal neutron will be larger, so that it more likely interacts with the nucleus. Therefore, area of cross section corresponding to these thermal neutrons will be higher. So the area around the nucleus, called the area of cross section, depends on various factors like nature of the incident particles, velocity or energy associated with the incident particles, and also on the intensity of the incident particles, and so on. Therefore, nuclear cross section can be defined, which is an interaction cross section, can be defined in such a way that it is the area around the nucleus facing the incident particles, within which the incident particles will lead to an interaction with the nucleus. Outside this area, incident particles will not interact with the nucleus. So, greater the nuclear cross section of the target nucleus, greater the likelihood of an interaction, and hence greater will be the likelihood of nuclear reaction. So all the three parameters go directly to each other. So it is greater the nuclear cross section of the target nucleus, greater the interaction, and greater the interaction leads to greater the nuclear reaction. This interaction cross-section area may be lesser or equal to or greater than the actual geometrical size of the nucleus. This is shown in this particular figure, which you can analyze from each of these cases. So in the first case, you can see as here represented, the lightened portion or lighter portion or lighter region indicates the interaction cross section, darkened region indicates geometrical cross section. So when you consider here the geometrical size of the nucleus and interaction cross section, in the first case, the lighter region being inside the actual size of the nucleus, geometrical size of the nucleus, you can see that here interaction cross section is smaller than the geometrical cross section of the nucleus. And in the second case, when you consider the size of the interaction cross section as well as the geometrical size of the nucleus are same, so both the circles are overlapping. And here in the third case, when you observe, the interaction cross section is larger compared to geometrical cross section of the nucleus. So the cross section of nucleus for a particular interaction is a mathematical way to express the probability that the interaction will occur when a certain particle is incident on the nucleus. So as you can see from the figure, you can consider that either the interaction cross section may be smaller than, equal to, or larger than the geometrical cross section. So this actually leads to derive an expression for number of incident particles involved in nuclear reaction, and also we can deduce the expression for nuclear cross section from it. So in this particular stage, with this diagram, we'll try to understand and we'll try to express an expression giving the relationship between sigma, that is nuclear cross section, and x, the thickness of the slab, and n naught, intensity of the incident beam, and so on. So here let us consider this diagram. Consider a thin slab of some material whose area is capital A and whose thickness is dx, as shown in the figure here. So here if you observe this figure, dx is representing the thickness and capital A representing the cross-sectional area of the slab under consideration. And with this diagrammatic representation, we'll try to deduce an expression for total number of incident particles involved in nuclear reaction, and hence the expression for sigma. So let the number of atoms or nuclei per unit volume in the slab or foil, you can consider as a foil also. Slab or a foil is represented by small n. Therefore, total number of nuclei in the entire volume of the slab is volume of the slab into number of atoms or nuclei per unit volume, that is n into volume, and small n into volume is represented by area into thickness. Area is A and thickness is dx. So area into thickness will give you volume of the slab, and volume into small n, which is representing the number of atoms or nuclei per unit volume, will give you total number of nuclei in the entire volume of the slab. So next we'll consider the cross-sectional area per nucleus per interaction is denoted by sigma, which is a nuclear cross-section. And once you have this cross-section representing per nucleus per interaction, then we have to calculate what is the aggregate cross-section of all the nuclei in the slab. So which is given by this cross-section per nucleus per interaction into total number of nuclei in the entire volume. So it is sigma into n into a into dx. So with this, we'll move on to the next step. So let us consider number of incident particles in a bombarding beam to be n. So if you go back to your figure, you can see that here this capital N is representing the total number of incident particles which is incident onto a target material, which is nothing but slab in our case here, and that is represented by capital N. Let the number of particles interacting with this nuclei in the slab is given by dn. So number of particles which are going to interact with the nuclei in the slab is taken as a small value, which is dn, so that we can write the ratio of interacting particles to incident particles, which will be equal to aggregate cross section by target area. So here interacting particles is nothing but small amount, which is denoted by dn, and the total incident particle is capital N, which should be equal to aggregate cross section is, just now we got it as sigma n into a into dx, substitute back here, divided by target area is total area, which is area of cross section capital A, so that the equation on the right hand side becomes sigma n into dx. Call this as equation 1. Consider the same beam of particles incident on slab of finite thickness x. Initially, we considered a small thickness dx, and we obtain the expression for dn by n here. If we extend the same for entire slab thickness, which is equal to x, finite thickness x, if each particle can interact only once, dn particles may be thought of as being removed from the beam in passing through the first dx thickness of the slab. So when we are considering dx as the thickness of the slab and we consider dn being the number of particles interacting, that indicates those particles are going to be removed from the incident beam. So that in the previous equation, we have to consider the minus sign. Since that many particles are being removed from the incident beam, passing through the thickness dx of the slab, we are considering it is associated with a negative sign. So in the equation 1, we write minus dn by n equals to sigma n into dx. Call this as equation number 2. So denoting the initial number of incident particles by n naught, we have to consider the previous equation with the integrals n naught to n. So here n naught represents the initial number of incident particle, capital N represents the total number of particles after the interaction, that is surviving particles, and they have to be the integration limits for this left hand dn by n term, and right hand side you are integrating between the initial thickness 0 to final thickness, that is total thickness x. So it is minus sigma n integral of 0 to x dx. So integrating and substituting the limits, you get the expression as ln n minus ln n naught, which is equal to minus sigma n x. Call this as equation 3. And so taking the exponential function on the right hand side, the left hand side becomes n, n naught is transferred to n naught, so n equals to n naught e to the power of minus sigma nx. So considering this particular equation, which is an expression for surviving particles, here n represents the total number of particles which are survived after the reaction, n naught represents the incident particles, and sigma represents the nuclear cross section, and x represents your thickness, and small n represents number of atoms per unit volume, which we considered in the beginning, number of atoms or number of nuclei per unit volume in the slab. So with that, we have an expression n is equal to n naught e to the power of minus sigma nx. So here, writing the expression from equation 2 for sigma, that is equation 2 is this negative sign equation. So from this equation, rewrite the expression for sigma. You can write it as minus dn by n dx, which is equal to probability of occurrence of reaction. So here minus dn by n tells you the probability of occurrence of the nuclear reaction divided by n into dx, and the unit for sigma standard SI unit is meter square. And here if we consider ndx, which is nothing but areal density of the atoms of the target. So areal density of the atoms of the target indicates total number of atoms per area, So it is considered to be unit value, then the unit nuclear cross section area, then we can define the cross section as it is defined as probability of occurrence of nuclear reactions per nucleus per unit area. So when we consider here in this expression ndx equals to of unit value, we can define sigma as it is the probability of occurrence of nuclear reaction per nucleus per unit area, or we can also define the nuclear cross section as the probability of interaction when single projectile particle is shot normally onto a target material containing a single nucleus per unit area. So with this definition of cross section area or nuclear cross section, we will move on to understand what is exactly the surviving particles. Surviving particles are nothing but the total number of particles which comes out of the target material after the interaction, such that it can be obtained by considering how many interacting particles are interacting with target nucleus with respect to the incident. So if I consider the previous expression 4 here, that is n is equal to n naught e to the power of minus sigma nx. Here, if the thickness x of the slab, if it is going to increase, since it is an exponential term with negative sign, indicates n is going to decrease with increase of thickness x. So the number of surviving particle will decrease if the thickness of the slab is going to increase by exponential sense. So that is what we consider under surviving particles, and with that we'll consider unit of cross section. So unit of nuclear cross section is popularly taken as Born. It is a famous unit which we use for nuclear cross section in all the problems or concepts related to nuclear cross section. And one Born is in symbol, Born is represented by B. So 1B or 1 Born equal 10 power minus 28 meter square, which is also equal to 100 Fermi meter square. So this unit of Born is taken as it is of the same order of magnitude as the geometrical cross section of the nucleus. So since it is so handy and it is going to resemble the magnitude of the same order of that of the geometrical cross section, the unit Born is taken into consideration. With that, we'll move on to problem. The cross section of cadmium 113 for capturing thermal neutrons is 2 into 10 power 4 Born. The mean atomic mass of natural cadmium is 112 units and its density is 8.64 gram per centimeter cube and 8.64 into 10 power 3 kilogram per meter cube. So find out what fraction of an incident beam of thermal neutrons is absorbed by cadmium sheet of thickness 0.1 millimeter, and in the second case what thickness of cadmium is needed to absorb 99% of incident beam of thermal neutrons. So here, when I consider first part, the solution, you have to consider out of the total naturally occurring cadmium 13 in nature, it is just cadmium 113 is just 12% of natural cadmium. So the number of 113 cadmium, that is 113 representing the mass of cadmium here. So cadmium 113 atoms per cubic meter is found by considering since it is 12% out of the total, n equals to 0.12 into density is given 8.64 10 raised to 3 kilogram per meter cube divided by its atomic mass, which is 112 units per atom. So convert that into in terms of kilogram by multiplying by 1.66 10 raised to minus 27 kilogram per unit. So total number of cadmium 13 atoms will become 5.58 into 10 power 27 atoms per meter cube. So once you know n, the capture cross section, that is interaction cross section, which is given by sigma, is 2 into 10 power 4 Born. It is given in the problem. So convert that Born into meter square. So it becomes 2 into 10 power minus 24. You know, one Born is 10 power minus 28 meter square. So substitute that, it will become 10 power minus 24 meter square. So the capture cross section sigma is 2 into 10 power minus 24 meter square. And find out the product of n into sigma. You can see that it is equal to 1.12 10 power 4 per meter. So we know that from the expression n is equal to n naught e to the power of minus sigma nx. So the fraction of the incident neutrons that observed is given by n naught minus n divided by n naught. So this is nothing but a fraction of incident neutron is nothing but which is being observed by the target material, that is dn by n naught. Dn is nothing but here n naught minus n. So n naught minus n by n naught will be equal to n naught minus n, you substitute in terms of n naught again. So it is n naught e to the power of minus sigma nx in the numerator divided by n naught. So simplify, you can write the expression in terms of 1 minus e to the power of minus sigma nx. Since we know x is of thickness 0.1 millimeter, convert that into meter. So it is milli is 10 power minus 3, it becomes 10 power minus 4 meter here, the value of x. So substitute all the values sigma nx in this particular expression, you will get n naught minus n divided by n naught, which is equal to 0.67. So here n naught minus n is nothing but dn by n naught represents the fraction of incident neutron that is being observed by the target material. So that it is comes out to be 0.67, that is 67%, or we can say in terms of 2/3 of the incident neutrons which are being observed. So we'll move to the second part. We have given 1% of the incident neutrons pass through the cadmium sheet. That means it is given in the problem that 99% of the incident beam of thermal neutrons being observed means 1% is passed through it. So we'll consider the second part. When we are considering 1% of the incident neutrons pass through the cadmium sheet, we can write the expression n, which is equal to zero point 0.01 times n naught. Since it is given 1% is surviving out of n naught incident particles, so n will be equal to 0.01 n naught. So from the expression n is equal to n naught e to the power of minus sigma nx, we can write n by n naught, which is equal to 0.01, which is equal to e to the power of minus sigma nx. And again here taking log or ln, it is ln of 0.01, which is equal to minus sigma nx. The exponential will become just minus sigma nx when you take ln on the right hand side. So here x is minus ln 0.01 by sigma n. Substitute for sigma n, and you have 4.1 into 10 power minus 4 per meter as the thickness, which comes out to be 0.41 millimeter, 0.41 millimeter. So cadmium is evidently a very efficient absorber of thermal neutrons. So only this much, when the thickness is this much, 1% of the particles are coming out means it tells you that cadmium is a good absorber material when thermal neutrons are being incident on it. So with this, we'll move to summary part of the session where you are going to revise what all the concepts you have learned so far. So you learned reaction cross section, the definition, the factors influencing it, and importance of it, that is significance of it, and also you derived an expression for cross section, and importance of it in understanding the variation of thickness and variation of the absorption. And also you worked out one problem to understand the concepts what you learned with respect to nuclear cross section. So references used for this particular session are Nuclear Physics by D.C. Tayal, Atomic and Nuclear Physics by Ghoshal, and Modern Physics by Arthur Beiser. And with this, I'm going to wind up this particular session. In the next upcoming session, I'm going to consider various types of nuclear cross section and what do you mean by reaction rate, and in detail you are going to learn the expression for it. And see you in the next class. Thank you. Thank you all.